welcome back. And today we start off our study of the second big section of calculus, integral calculus. And in order to gain a little intuition as to what an integral is, we start off with this little word problem here. You can read along with me. We got Sam here biking from his home, and he's going due west. So he's biking in a straight line, as all our first-year calculus problems are, straight line motion. He's going due west at the following pace. He goes a half mile per minute for the first 30 minutes. Okay, so he starts off at a pretty brisk pace. Then after the first 30 minutes, he slows down a bit and goes 0.3 miles per minute for the next 20 minutes. Then he stops for 10 minutes for a snack break. And after that, after his break, he comes out raring to go, and he's pedaling faster at 0.8 miles per minute for the next 60 minutes. And now what we get asked a question here. The first question being, how far is Sam away from home 45 minutes into his route? And then what about after 1.5 hours? Or I guess I'd translate that into 90 minutes. Now, even knowing nothing about integrating, we're going to I bet we could figure this out. It looks like for the first 30 minutes, he goes, for the first 30 minutes, I'm talking about question one, I guess, A1. This is question 1. I guess we'll call this question 2. For question 1, he goes, 30? We kind of know distance, this is underlying this. Distance is equal to rate times time, right? And he goes 0.5 miles per minute times 30 minutes, okay? Plus then, plus 15 minutes at whatever his second pace is, 15 minutes. And what was the second pace? It was 0.3 miles per minute, 0.3. You see the units cancel, we're adding up miles here. So it looks like we get, this is 15 plus 15 plus 4.5. So we're going to get 19.5 miles. Notice the units add up, right? The minutes cross out. Miles times minutes times minutes per mile, I get miles. So the units are miles. Okay, how about second problem? We could do the second one, I think. We go 90 minutes. Well, 90 minutes, we're going to do what? Ooh, looks like we got, once again, we got 0.5 times 30. I'll get rid of the units now. Times 30 plus 0.3 times 20 times 20. Then 10 minutes, we go 0. Plus 0 times 10 plus, let's say I got 30, I got 60, plus I got 30 minutes running at the big pace here of 8.8 miles per minute. And how far is that? That's going to be 15 plus 6 plus 0 plus 24. That looks to me, if I did everything right, that looks like about 45 miles. Ooh, that's pretty good. That's a pretty good pace for 90 minutes. 90 minutes, okay. That guy he was booking pretty good. Okay, so anyway, we're adding things up. We're adding little units of miles per minute times time. Now, So I think in the previous slide, you could have figured out that word problem without any concepts of calculus. But I'm going to make this look more like a typical calculus problem. And I'm going to model, Sam's ride here, okay? And here's my function. I get a function, I'm going to call it velocity of t. And notice here he's going what? He's going 0.5 miles per minute for the first 30 minutes. Then he goes from 30 to 50 minutes. He's going to go 0.3 miles per minute. Here he takes his lunch break right here. There's lunch. And then up here, we're going to, he books it for 0.8 miles per minute. And why don't I erase this part? Now let's see what this looks like. If we were going to work this problem now, question 1, he's out for 45 minutes. Okay, so he basically what we're doing is we're multiplying. Oops. Let's see, I better get my thing back here. Maybe I'll fill this in with red, but you take 30. It's supposed to go 30. And if you look at the area under there, the area is going to be the height, which is 0.5, right? 0.5 times 30, that's going to be 15. Better put this in as that's underneath that curve there. If we multiply the velocity times the time, notice we're in minutes here, we're going to get 15 miles under that first curve. Then if we go 45, we go out here to like 45. And we'll go red again, I guess. And we add up that area too. And we got what? 15 minutes times, and we're going to get 4.5. So this question, we effectively add up the area under this curve. We add up the velocity times time, and we're going to get 15 plus 4.5. We're going to get 19.5 miles. Question 2, right? Question 2 went all the way out to 90. Went to 90, so it went out to here. Out to here. And here you see we're going another 20. Let's erase this. When I go question 2, I've got all this area here, which is what? Here's 20 times 0.3, that's 6. That's 6. I've got 0 area under this curve. And then here, I've got this area. Area under the curve, right? It's going to be the height of the curve, which is going to be velocity, in miles per minute, times the heights in miles per minute. The width is in minutes. So I'm adding up miles under the curve here. This now is what? This is 90. So this is 30 times 0.8. That is going to be 24. So for question 2, I add up these numbers and I get 15 plus 6 plus 24. I get, as I did before, 45 miles. So you can see here that we can answer these questions that you could have done without calculus by getting a functional description of velocity and adding up kind of the area under the curve. And the area of under the curve, if it's all positive, will give us distance. So this is what we're going to get to. We're going to have a little symbol that looks like this. We're going to say the integral, for instance, for question 2. Would be really the integral from 0 to 90. We would integrate the velocity of t times dt. And we would add up, this is what? Miles per minute, the units. dt, well, we're going to have to explain what that is. That's in minutes. These are little rectangles we're going to add up. And this is the area. This represents the area under the curve. Now these are nice rectangles here. Easy to add up areas. That won't always be the case. We could model, for a more realistic model, we might draw a little curvature in this. You know, when Sam's writing, he's not really a perfect, he's not perfect, and he does slow down, and he ripples here, and then he goes down to launch. He doesn't slow down right instantaneously, and then he kind of speeds up like that, and he doesn't keep it constant. So that might be a more realistic model in blue. If we could still do the same concept though. If we wanted to know how far he traveled in 90 minutes, well, how would we find this answer? We could add up little rectangles. We'd add up. We're trying to find, it's still the area under this curve, and we might find this. If we found the area under the curve and calculated the total area, including these round spots, everything under the curve all the way out to 90, the area under the curve would be the distance that Sam has traveled. And that is what we're going to be talking about. When we talk about integral calculus, we're going to be adding up little changes to calculate things like distance traveled. Okay, in the next slide, we'll get a little more formal about how we might start with approximating the area under this curve, and we'll draw a general function, and we'll approximate by finding the areas of rectangles. Okay, we'll see you soon.